The researchers determined that human Neanderthal interbreeding actually occurred 100,000 years earlier.
You probably don't think much about Neanderthals when it comes to sex, but maybe you should. Because buried in your DNA right now are fragments of ancient hookups that happened tens of thousands of years ago. Neanderthals didn't just live alongside our ancestors, they got intimate with them. And the evidence of those encounters is written in our genes, telling a story that's far stranger and more complicated than anyone imagined.
The latest scientific evidence on the Neanderthals is that they were symbolic creatures. Certain populations in the world today still have 3 to 5% of Neanderthal DNA.
Who were the Neanderthals, really? Before we dive into the bedroom activities of our extinct cousins, let's get one thing straight. Neanderthals weren't the dim-witted cave brutes that old cartoons made them out to be. These were sophisticated humans, just a different species. They lived across Europe and parts of Asia for around 400,000 years before disappearing about 40,000 years ago. Physically, they were stocky and muscular, built for cold climates with barrel chests and shorter limbs. Their brains were actually slightly larger than ours, though shaped differently. They stood between 5'4" and 5.6 on average, with prominent brow ridges and faces that jutted forward more than ours do. But they weren't monsters. They buried their dead, made jewelry, created art, and used complex tools. Neanderthals lived in small groups, probably 10 to 30 individuals, and their lifespan was roughly similar to early humans, around 30 to 40 years if they survived childhood. They hunted large game, gathered plants, and controlled fire. Archaeological sites show they occupied the same caves for generations, suggesting stable social structures. This wasn't a species just scraping by. They were successful, intelligent, and remarkably human. The DNA bombshell, we had sex with them. The story changed completely in 2010. That's when scientists sequenced the Neanderthal genome and compared it to modern human DNA. What they found was shocking. If you're of European, Asian, or Native American descent, about 1 to 4% of your DNA comes from Neanderthals. The only people without this genetic legacy are those with purely sub-Saharan African ancestry, which makes sense because Neanderthals never lived in Africa. This wasn't just background noise or genetic coincidence. It was clear evidence that Homo sapiens and Neanderthals had interbred, and those hybrid children survived, reproduced, and passed on Neanderthal DNA that persists to this day. The implications were massive. It meant that the story of human evolution wasn't a simple line of one species replacing another, but a messy web of interactions, migrations, and yes, sex. The interbreeding likely happened in the Middle East and Near East regions, where the two species first encountered each other as modern humans migrated out of Africa between 50,000 and 70,000 years ago. Fossil evidence and genetic data point to places like the Levant, modern-day Israel, and Lebanon as early contact zones. But it didn't stop there. Evidence suggests multiple encounters happened across Europe and Asia over thousands of years as the populations overlapped. What's particularly interesting is that we find different Neanderthal genetic variants in different modern populations. East Asians carry slightly more Neanderthal DNA than Europeans, suggesting separate interbreeding events as humans spread eastward. The genetic signatures tell us these weren't isolated incidents, but recurring encounters across vast distances and time periods. How often did humans and Neanderthals hook up? Here's where it gets really interesting. At first, scientists thought maybe this was a one-time thing, a brief period of interbreeding followed by separation. But the genetic evidence tells a much more complex story. There were multiple waves of interbreeding spanning thousands of years. The first major pulse happened around 50,000 to 60,000 years ago, when modern humans first left Africa and encountered Neanderthals. But that wasn't the end of it. Genetic analysis reveals at least 3 to 4 distinct periods of gene flow between the populations. Some researchers have identified evidence of interbreeding as recently as 37,000 years ago in Romania, where a fossil known as OAC1 shows recent Neanderthal ancestry just 4 to 6 generations back. This means that whenever these two species shared territory, they were apparently willing to mate with each other. Given that this happened across tens of thousands of years and thousands of miles, it wasn't rare. The populations were small, though. Neanderthals probably never numbered more than 70,000 individuals across their entire range, and they were spread thin. Modern humans, on the other hand, came in larger groups with faster population growth. The math suggests that even occasional interbreeding, maybe just 1 or 2% of mating events, would be enough to leave the genetic signature we see today. But occasional over 10,000 years adds up. We're talking about countless individual encounters, relationships that lasted long enough to produce children, and communities that accepted these hybrid offspring enough that they survived to reproductive age. The mechanics, could they even reproduce together? This raises an important question. How were they even compatible? Different species usually can't produce fertile offspring together. Horses and donkeys can mate and create mules, but mules are sterile. Lions and tigers can produce ligers, but they have health problems. So what made humans and Neanderthals different? The answer lies in how recently we diverged. Humans and Neanderthals shared a common ancestor about 500,000 to 600,000 years ago. That's recent in evolutionary terms. We were still similar enough genetically that our reproductive systems were compatible. We had the same number of chromosomes, and our DNA was about 99.7% identical. That tiny difference was enough to make us separate species with distinct physical and behavioral traits, but not enough to create reproductive barriers. The evidence proves that hybrid offspring weren't just viable, they were fertile. If they'd been sterile like mules, their Neanderthal DNA wouldn't have spread through the human population. Instead, these hybrids had children of their own, and those children had children, continuing down to the present day. There's even evidence that some genetic combinations might have been problematic. Neanderthal Y chromosomes and mitochondrial DNA, which pass down through male and maternal lines respectively, have completely disappeared from modern humans. This suggests that hybrid males might have had reduced fertility, or that mitochondrial mismatches caused problems. But clearly, enough successful reproduction happened to leave a lasting mark. Neanderthal mating behaviors and courtship. So what were Neanderthal relationships actually like? We'll never know for certain, but the evidence gives us clues. First, sexual dimorphism, the size difference between males and females, was relatively small in Neanderthals, similar to modern humans. In species where males are much larger than females, like gorillas, you typically see harems and intense male competition. In species with less dimorphism, like us, you see more pair bonding and cooperative parenting. Archaeological evidence supports this. Neanderthal sites show individuals of different ages living together, suggesting family groups. The care of elderly and injured individuals, evident from healed fractures and survival despite disabilities, points to strong social bonds and cooperative behavior. These weren't creatures driven purely by instinct. They had relationships. Some sites provide tantalizing hints of more. Cave sites in France and Spain have revealed what might be decorative objects, ochre pigments potentially used as body paint, and collections of shells and feathers. While we can't prove these were used in courtship, it's not a stretch. Modern humans use decoration and display to attract mates. Why wouldn't Neanderthals? The overlap zones between Neanderthals and humans also tell us something. If the two species fought constantly or avoided each other, we'd see archaeological evidence of conflict or clear territorial separation. Instead, we see sites where both populations lived, sometimes at different times but occasionally overlapping. They shared the landscape, and apparently they interacted peacefully enough for romantic relationships to develop. Given that viable offspring resulted from these unions, there must have been some form of communication and mutual consent. These weren't likely violent encounters. They were relationships that developed in shared territories, possibly driven by curiosity, attraction, or simply the practical needs of small, scattered populations looking for mates. Inbreeding and small population problems. While humans and Neanderthals were mixing it up, Neanderthals faced a darker problem within their own populations: inbreeding. Genetic analysis of Neanderthal remains has revealed unusually low genetic diversity, suggesting small, isolated populations that frequently mated with close relatives. A jawbone found in Altai, Siberia, belonged to a Neanderthal woman whose parents were either half-siblings or an uncle and niece or grandparent and grandchild. The inbreeding coefficient was incredibly high. This wasn't an isolated case. Analysis of other Neanderthal fossils shows similar patterns of low genetic diversity and evidence of inbreeding depression, the accumulation of harmful recessive genes. Small population size made this almost inevitable. With groups of 10 to 30 individuals scattered across vast territories, finding an unrelated mate was difficult. Over generations, this took a toll. Inbreeding reduces fertility, increases infant mortality, and can cause developmental problems. It makes populations more vulnerable to disease and less adaptable to environmental changes. This was likely one of the factors that made Neanderthals vulnerable to extinction. As their populations dwindled and became more fragmented, inbreeding would have accelerated their decline. Ironically, interbreeding with humans might have provided a genetic boost to the hybrid offspring, giving them access to a larger, more diverse gene pool. The small amount of Neanderthal DNA that survives in us today might represent the successful genetic legacy of a species that couldn't maintain itself independently. The Denisovan connection, it gets weirder. Just when you thought the story couldn't get more complicated, enter the Denisovans. Discovered through DNA extracted from a finger bone in a Siberian cave in 2010, Denisovans are another extinct human species that lived in Asia. We don't have many fossils, mostly just fragments, but their DNA tells an incredible story. Denisovans interbred with both Neanderthals and modern humans. Genetic analysis shows that some Neanderthals carried Denisovan DNA, meaning those two species had sex and produced hybrid offspring. Meanwhile, modern humans also interbred with Denisovans, and that DNA persists today primarily in Melanesian, Australian Aboriginal, and Southeast Asian populations, making up 3 to 5% of their genomes. Here's where it gets wild. There's evidence of a three-way genetic mixing. Some human populations carry DNA from both Neanderthals and Denisovans. Even more bizarre, there's evidence of ghost populations, unknown human species that interbred with Denisovans before Denisovans met modern humans. A fossil found in Denisova Cave belonged to Denny, a teenage girl who lived 90,000 years ago. Her mother was a Neanderthal, and her father was a Denisovan. She was a first-generation hybrid. This paints a picture of the ancient world as a place where multiple human species coexisted, overlapped, and regularly interbred whenever they encountered each other. It wasn't a simple story of replacement, but a complex web of interactions. What Neanderthal DNA did to human sexuality. So what did we actually get from Neanderthals? It's not just random junk DNA. Some Neanderthal genes are under positive selection, meaning they provided advantages to modern humans and increased in frequency over time. Others, however, have been selected against and are rare or absent in specific parts of the genome. Interestingly, several Neanderthal gene variants affect traits related to reproduction and sexuality. Some genes influence skin and hair characteristics, which could relate to sexual selection and attractiveness. Others affect hormone regulation, including genes involved in testosterone production and estrogen signaling. Research has identified Neanderthal DNA variants associated with progesterone receptors, which play crucial roles in pregnancy and the menstrual cycle. Some of these variants are more common in certain populations and might affect fertility, miscarriage risk, or hormone-related conditions. There's also Neanderthal DNA linked to pain tolerance and even the timing of puberty. One particularly fascinating finding involves genes related to immune system function, especially those dealing with pathogens encountered outside Africa. Neanderthals had lived in Europe and Asia for hundreds of thousands of years, adapting to local diseases. When modern humans arrived from Africa, they lacked these adaptations. Interbreeding with Neanderthals provided a shortcut, giving incoming humans genes already fine-tuned to fight local infections. However, not all Neanderthal DNA was beneficial. The X chromosome, which carries many reproduction-related genes, has significantly less Neanderthal ancestry than other chromosomes. This suggests that many Neanderthal variants on the X chromosome reduced fertility in hybrids and were eliminated by natural selection. Similarly, testis-specific genes show depleted Neanderthal ancestry, hinting at incompatibilities that affected male fertility. Why did we outbreed them? If Neanderthals and humans could interbreed and produce fertile offspring, why did Neanderthals disappear while we thrived? The answer probably comes down to demographics and population dynamics rather than any single dramatic event. Modern humans had larger population sizes and faster population growth, even a small reproductive advantage, better infant survival rates, shorter intervals between births, or slightly longer lifespans would compound over generations. Archaeological evidence suggests modern humans had more diverse diets, more sophisticated hunting strategies, and wider trade networks. These factors would support larger, more stable populations. Neanderthals, already struggling with small population sizes and inbreeding, were at a disadvantage. When the two populations encountered each other, genetic mixing went both ways, but the flow was asymmetric. Because humans outnumbered Neanderthals, even equal rates of interbreeding would mean Neanderthal genes got absorbed into the larger human population rather than the reverse. Climate change during this period also played a role. Neanderthals were adapted to cold climates, but the period between 50,000 and 30,000 years ago saw rapid climate fluctuations. Modern humans, with more flexible technology and social structures, might have adapted better to these changes. As Neanderthal populations shrank and fragmented, the influx of human genes through continued interbreeding would have further diluted Neanderthal genetic identity until they effectively vanished as a distinct population. The evidence we carry in our DNA tells us something profound about human nature. When our ancestors encountered other types of humans, they didn't just fight or avoid them. They formed relationships, had children together, and created a legacy that lives on in billions of people today. Those ancient encounters in caves and campsites across Ice Age Europe weren't just footnotes in history. They shaped who we are, influencing everything from our immune systems to our fertility. Every time scientists analyze ancient DNA, the story gets weirder and more interconnected, reminding us that being human has always been more complicated than we thought.